Hi everyone, welcome to the session on SQL Server architecture. Today, we will explore how SQL Server works under the hood from the network interface all the way to data storage, caches, and memory management. By the end, you will understand how your SQL statements like select, update, and delete interact with SQL Server internally. Let's deep dive in. So, on the screen, you are able to see the architecture diagram of SQL Server. This is how it will work. We have SNI layer and the protocol layer and relational engine. Then comes to the storage engine and we have a cache. So we will discuss by one. Let's go to the page which I created. This is SQL Server architecture workflow diagram. Okay. In this, we will learn everything over here. So in this way, each diagram is interactive, shows real timing information that you will encounter in production environments. By the end of the session, you will understand exactly how your SQL queries flow through SQL Server's sophisticated architecture. Let's start with a big picture. So we are going with the SQL Server architecture overview. So at the top, we have client application. This could be a SQL Server Management Studio or your application which has C Sharp or Java or web APIs. Every query starts here. Then now from here you can see the arrow mark. Now it is going to SQL Network Interface. In SQL Network Interface, this SQL Server is a communication layer. It handles network protocols like TCP, IP, and named pipes. Then coming to connection management and authentication and all the packet processing. Now it goes to once this is done, it will goes to protocol layer. This is where SQL Server understands the tabular data stream protocol and then passes your query or commands, manages your session state. Then it will reach the heart of the SQL Server, the relational engine. This is where the magic happens. Your SQL gets passed and validated. The query optimizer creates execution plans. The query executor runs those plans and the plan cache stores them for the reuse. Finally, we have the storage engine which handles buffer pool for memory management, physical data access, the transactional management, all the disk operation. This layered approach is crucial for performance, scalability, and maintainability. Each layer has a specific job, they work together seamlessly. Now, let's deep dive deeper into the first layer, the SNI layer or SQL Network Interface layer. SNI supports multiple network protocols and it is automatically chooses the best one. The first one is TCP IP is most common for network connection and comes to network named pipes for local Windows connection and comes to shared memory. It is actually the fastest but only works on the same machine. Then comes to VIA for specialized high performance hardware. And we have connection management is critical for performance. SNI handles the connection pooling to reduce overhead, SSL TLS encryption for security, authentication integration with Windows and SQL Server modes, then timeout handling and connection cleanup. Now, let's look at the actual processing flow. Notice the timing information on the right. This is SNI workflow. The step 1 takes about zero point 0.1 millisecond. The client sends a connection request and SNI receives it, and it validates the protocol and starts the authentication. Now comes to the authentication, which is step 2. Step 2 is variable timing because authentication takes different amount of time. Windows authentication using keyboards or NTLMS is faster than SQL Server authentication. Once this authentication is done, it will go to step 3. Step 3 is another zero point 0.1 millisecond for packet processing. SNI enables fragmented network messages, performs error detection, and manages workflow control. These timings might seem small, but remember, every query goes through this process. When you are handling thousands of queries per second, these microseconds adds up. Then we are going into the protocol layer. This is where SQL Server starts understanding what you want to do. The tabular data stream responsibility is a SQL Server native language. It standardizes how messages are formatted between client and server, how different data types are handled, how results sets are structured, how batches of commands are processed. Then the command processing components is doing several critical things. It identifies what type of SQL statement you sent, whether select, insert, update, and delete. It handles parameter binding for prepared statements. It separates batches when you send multiple statement. It detects transactional boundaries. Then comes to we have what to say each application. So each application connects differently. We have different types of connection strings, which is ODBC handler for legacy applications, OLEDB handler for form based application, ADO.NET handler for .NET application using SQL client, and we have JDBC handler for Java applications. And we have a session management under protocol layer. This session management maintains your connection state, transaction context, very important for data consistency, user permissions that were validated at connection time, session specific variable and settings. This layer is often overlooked, but it's crucial translation work. It's doing a crucial translation work. It's converting your application's request into SQL Server's internal format, and it's maintaining all the context needed for your session. Then we are going into the third one, which is relational engine. Now we are in heart of SQL Server, that is relational engine, also called the query processor. We have a query processing pipeline. Every query goes through these exact steps. Step 1 will take 1 to 2 milliseconds. Parser does detailed syntax checking. It's much more thorough than what happened in protocol layer. Then comes to algebraizer, then resolves all your table column names and validates permissions through algebraizer. Once this step 1 is done, it will move to step 2. Step 2 is where the magic happens, query optimization. This can take 2 to 30 milliseconds, and here is why that range is so wide. The optimizer performs cost based optimization. It analyzes statistics about your data, evaluates which indexes to use, chooses join algorithms, and generates multiple possible execution plans, selects the one with lowest estimated plan. For complex queries with multiple join, this can take another significant time, not only 0 to 2 to 30 millisecond, it will take much more significant time, but it's time well spent because a good execution plan can make the difference between a query running in millisecond versus minutes. Then once step 2 is done, it will go to step 3, which is query execution engine. This is where the plan actually gets executed. It will take 1 to 15 milliseconds depending on the complexity. The execution engine retrieves the plan from the cache if available, creates an execution context with your specific parameter values, then executes each operator in the plan, and it will coordinate with the storage engine for actual data access. Let's look at these execution operators. These are building blocks for every execution plan. Let's look on data access operators, which have four operators. One is table scan, reads every row, usually expensive, and comes to index scan, reads all rows in an index, better than table scan. Then index seek uses the index to find specific row. This is what we want. And key lookup retrieves additional columns not in the indexes. This is what data access operator will do. Then let's learn about join operators. Join operators handles how tables are combined. Nested loop is efficient for small datasets. Hash join works well for larger datasets. Merge join is perfect when data is already sorted. Apply join will work only on correlated subqueries. And coming to the processing operators, this handles other operations like sort for data for order by clauses, filter for where conditions, aggregate for group by operations, top for limit or top clauses. Now let's talk about plan catchy. This is a huge performance multiplier. Compiled plans are ready to execute plans with all operator details. When SQL Server finds a matching plan in a cache, it can skip the entire optimization phase. That's saving of 20 to 40 milliseconds per query. Then comes to ad hoc plan. This created for non-parameterized queries. These can cause problems because each validation of literals creates a new plan. For example, where id equal to 1 and where id equal to 2 would create separate plans. Then comes to prepared plans. Prepared plans are much better. These use parameters, so one plan can handle many different values. This is why using parameterized queries is so important for our performance. So this is about relational engine. Now we are going into storage engine. Finally, we reach the storage engine where your data actually lives. Buffer pool is the SQL Server's main memory cache. Look at this layout. We have data cache, index cache, and free memory pool. These are the layouts available inside the buffer pool memory. The data cache stores 8 KB data pages in memory. It uses LRU algorithm. Least recently used pages gets removed first when memory is needed. Then coming to index cache, the index cache stores index pages for fast lookups. These B-tree structures are crucial for query performance. The memory pool, which is the free memory pool, is available for allocation. SQL Server dynamically manages memory between these different users. Now let's understand page states. This is crucial for understanding SQL Server behavior. Clean pages are unmodified. They match exactly what's on disk. These can be removed from memory at any time without data loss. Dirty pages have been modified in memory but not yet written to disk. These are critical for performance but also for recovery. SQL Server must write these to disk eventually. Free pages are available memory slots for new data. Then coming to access method, this access method can handle row level operations unlocking, index key seeks and scans, constraint validation, row versioning for different isolation levels. This transaction services ensures ACID properties, lock management with different lock types, transaction lock maintenance for durability, deadlock detection and resolution, ensuring consistency across concurrent operation. Then coming to background processes, we have a lazy writer which frees clean pages when memory is needed. Checkpoint writes dirty pages to disk regularly. Log writer manages the transaction log writes. Understanding these processes helps explain why sometimes queries might be slower. They might be waiting for memory or a checkpoint to complete. Now we have a three example for select statement flow, update flow and delete flow. Coming to the select flow. Now for example, we are running a query called select customer name email from customers where city equal to London. Now this select statement, how it will run through SQL Server architecture. That's what we are going to learn about. So step 1, SNI process the network packet in zero point 0.1 millisecond. Connection is validated. TDS packet is processed, passed, and it is going into the protocol layer. The protocol layer identify this is select statement and retrieves session context, does basic validation, another for zero point 0.2 millisecond. Then it is going into parser and algebraizer. It will do detailed validation whether table exists, column exists, do you have select permission, all good, then which took 1.22 millisecond. Now it will go to query optimizer which takes 2 to 30 milliseconds. This is where time varies depending on the complexity. It checks the plan cache first. If there is an existing plan, we can reuse and save 20 to 40 millisecond. If it is a new query, the optimizer evaluates indexes on the city column and decides between the index seek versus a table scan. Once that is done, it will go to the query execution engine, which takes 1 to 15 milliseconds. It creates an execution context, executes each operator in sequence. Then it will go to step 6. Over here, we are actually gets the data. This timing varies dramatically based on whether pages are in the buffer pool or needs to be read from disk. Cache hit 0.01 milliseconds, data already in memory. Cache miss 5 to 15 millisecond, then must read from the disk. So total time which it took is 5 to 65 millisecond. The wide range depends on plan cache hits and buffer pool cache hits. Well organized queries with proper indexing typically complete this under 10 milliseconds. Now coming into update flow. So we have update customer set email equal to new email where customer ID equal to 1235345. Now we are updating a customer's email ID using customer ID. Now what will happen? Now from step 1 to 3 are similar to select but with additional update permission check. The execution plan includes locating a row, modifying it, and updating any affected indexes. Then comes to step 4 is a new the transaction begin. This takes 1 to 3 milliseconds in SQL Server. Start an implicit transaction, then writes a begin record to the transaction log, requires exclusive logs on the target row. Once that is done, this is actual data modification which takes 2 to 8 milliseconds. Locates the target row using primary key very fast, logs the before image for rollback capability, then modifies the row in buffer pool, creating a dirty page, logs the after image for recovery, then updates any affected indexes. Then it will come to the sixth step. It will take 1 to 3 milliseconds, writes commit record to transaction log, releases all logs, returns one row affected, dirty pages remain in buffer pool for the next checkpoint. The log management is crucial for data integrity. Exclusive log on modified row prevents other transactions from changing it. Intent logs on the page and table. Logs are held until the transaction gets committed. The performance breakdown. Primary key lookup 1 to 2 millisecond very fast with proper indexing. Index maintenance 2 to 5 milliseconds per affected index. Transaction log write 1 to 3 milliseconds. Totally 5 to 15 milliseconds. This is why having proper indexes on frequently updated column is so important. Now we are going into the last, which is delete flow example. So delete operations can be most complex, especially when deleting many rows. This deletes old cancelled records, potentially thousands of rows. We are given the status is cancelled and we have given this order date also. We need to delete all the orders cancelled before 2022 on January 1, 2022. Now step 1, we have query optimization is more challenging, which takes 5 to 50 milliseconds. Multiple where conditions make index selection complex. potentially large result sets, and multiple indexes to consider. Foreign key constraints must be validated. One, then it will go to step two, row location and locking. It will be a variable timing. May require index can if there is no perfect index. Could affect thousands of rows. Each row needs an exclusive lock. Potential lock escalation to table level for larger deletes. Then step 3 is for constraint checking. Has high impact because all foreign key relationships must be verified. Then cascading deletes are processed if configured. Referential integrity must be maintained. Check constraints are validated. Then going to step 4, all indexes on the order table must be updated. Entries for deleted rows are removed. B tree what we call rebalancing may be necessary. Statistics may be updated. Then we are coming to step 5. Each deleted row is logged individually. Large data sets, large deletes generates massive log activity, may require log backups during the operation. Log growth monitoring becomes crucial. Coming to the performance characteristics, performance scales dramatically with row count. Small deletes like under 100 rows can take 10 to 50 milliseconds, which is very manageable. And coming to medium deletes, less than deletes of 1000 rows may take 100 milliseconds, which have like noticeable impact. Large deletes like 100k plus rows, minutes or longer, considered batching these operations. When doing a large delete, buffer pool, we are going into buffer pool impact. Many pages must be loaded for scanning. High dirty page generation from modifications. Memory pressure is possible. Increased checkpoint activity. And coming to the optimization strategies, proper indexing on where clause columns, considered batching large deletes into a smaller chunks. For example, we have 1 lakh rows, we can consider batching into 5,000, 5,000, 5,000 rows. So it will come under medium deletes, which can be a manageable one. And comes to schedule large deletes during low activity periods. Let's wrap up with the key takeaways from our architecture deep dive. Understanding this flow helps you. For performance optimization, writes a query that leverage the plan cache efficiently. Understand why parameterized query perform better. Know when buffer pool hits matter most. Recognize why proper indexing is crucial. And for troubleshooting purpose, identify whether slowness is an optimization or execution. Understand the impact of memory pressure. Recognize log contention parameters. Know when transaction log activity affects performance. For the best practices, use parameterized queries for plan cache efficiency. Monitor page life expectancy for buffer pool health. Design indexes based on your most critical queries. Understand the cost of large modification. Every component we have discussed works together. The SNI layer ensures reliable communication. The protocol layer handles session management. The relational engine optimizes and executes queries. And the storage engine manages your data efficiently. These interactive diagrams are available you to explore further. Each component we discussed plays a vital role in SQL Server performance reliability. Thank you for joining in SQL Server architecture. Understanding these internals will make you more effective database developer and an administrator.